For the last 3 years, we have been building software under a flawed assumption that human beings would always be the primary consumers of AI outputs. We built chat windows, clean UI dashboards, human-in-the-loop validation checkpoints. Welcome back to AI Dev Guy. Today, we are breaking down the complete structural demolition of that design paradigm. As we cross deeper into 2026, the tech industry is quietly undergoing a massive architectural migration toward decentralized, autonomous mesh networks. Google's open-source A2A, the agent-to-agent protocol, is gaining massive momentum. We are entering an era where specialized agents, running in completely separate developer environments, using entirely different model weights and host infrastructure, are talking, negotiating, and delegating complex multi-step tasks directly to each other. And do not confuse this with MCP. The Model Context Protocol connects a single agent downward to its tools, its databases, its files, its functions. A2A connects agents sideways to each other as peers. MCP gives one agent hands. A2A gives 1,000 agents a shared language. Think about the scale of this shift. Instead of a developer writing rigid, static REST API endpoints to pass JSON data from an authentication app to a database worker, you deploy a sovereign agent. That agent autonomously identifies another specialized agent on the network, negotiates execution rights, passes an asynchronous payload, and awaits a non-deterministic result. Picture the topology in practice. A planner agent built on LangGraph decomposes a goal. It hands the research leg to a crew AI crew running on one cloud and the implementation leg to an autogen coder running on another. 3 frameworks, 3 vendors, 3 model families, 1 coordinated task, and not a single hard-coded integration between them. But building a system where software is entirely composed of algorithms, talking to algorithms, introduces a brutal checklist of distributed systems nightmares. How do you handle asynchronous retry semantics when an autonomous node goes dark? How do you maintain an immutable logging audit trail when a single prompt triggers an invisible cascade of 100 sub-agent loops? Today, we look past the surface of the basic chat wrapper and log directly into the real infrastructure mechanics of the multi-agent mesh. To understand how a multi-agent mesh functions, we have to look directly at the telemetry of the A2A handshake. In a traditional software stack, integrations are explicitly hard-coded. If App A wants to talk to App B, you authenticate with a static API key, format the payload exactly to a strict OpenAPI specification, and parse a predictable response status. In an A2A protocol environment, that rigid structure disappears. The process relies on 3 architectural primitives: discovery, negotiation, and execution. So how does one agent even know another exists? Every A2A-compliant agent publishes a machine-readable agent card, a small manifest served at a well-known address that advertises exactly what it can do, its skills, its input and output formats, and the authentication it demands before it will lift a finger. When Agent A runs into a boundary constraint, say it needs to execute a complex cryptographic audit but only has access to a lightweight local model, it broadcasts a capability discovery request to the local mesh network. It asks, who has access to verified SecOps tools and a high-context execution sandbox? An independent specialized agent on the mesh, Agent B, responds with its structural capability profile. But they do not just instantly execute the task. They negotiate. The agents pass cryptographic handshake tokens that establish semantic boundaries. What is the exact scope of the task? What are the hard limits of token consumption or compute allowed? And what identity credentials verify that this agent is even authorized to touch this system's context? And A2A does not model this as one blocking request. It models it as a task with a lifecycle. A task is submitted. It moves to working. It can pause at input required when the worker needs more from you. and it terminates as completed, failed, or canceled. The parent does not freeze a thread. It tracks a state machine. Once the capability and identity metrics match, a temporary secure state channel opens over local WebSockets or gRPC streams. The task is delegated, and the parent agent drops into an asynchronous listening loop. Here is what the actual call looks like. The client opens a structured request, a message broken into typed parts, text, data, or a file reference, and posts it to the worker's endpoint. No bespoke SDK per partner. One envelope format that every compliant agent on the mesh already knows how to parse. For long jobs, the worker does not make you wait in the dark. It streams. As it thinks, calls tools, and produces partial output, it pushes incremental updates back over a live channel using server-sent events. And if the parent disconnects, A2A falls back to push notifications, a webhook the worker calls the moment the task finally lands. The integration did not exist when you booted up the server. The software generated the connection dynamically, out of thin air. Now let's talk about where this architecture completely breaks down in production: non-deterministic state lifecycles and volatile retry semantics. In traditional backend engineering, if an API call fails, the handling is straightforward. You get an HTTP 429 for rate limits or a 500 for a server error. You configure an exponential backoff policy, wait 3 seconds, and try again. But what happens when your API endpoint is an autonomous agent that does not return a predictable error code, but instead returns an unexpected, hallucinated sentence or an incorrect tool argument execution? If Agent B encounters a tool failure midway through an operation, it might try to self-correct. It loops internally, consuming compute, spinning up its own sub-agents, and blowing past your execution windows. Start with the rule every distributed systems engineer learns the hard way. If a request can be retried, it will be retried. So every delegated task must carry an idempotency key, a unique fingerprint that lets the worker recognize a duplicate and return the original result, instead of executing the same destructive action twice. Because the network only ever gives you at least once delivery, never exactly once. That timeout you saw did not mean the work failed. It might have completed. The acknowledgement just got lost on the way back. Fire a naive retry, and you have now run the same database migration twice. Idempotency is what turns at least once into effectively once. If you apply traditional backoff loops to an A2A mesh, you run directly into a systemic cascade timeout. If parent agent A times out while waiting for worker agent B, it might assume the packet was dropped and fire off an identical request to worker agent C. Suddenly, your mesh network is flooded with redundant, resource-intensive multi-agent loops that are completely out of sync, eating your compute margins and filling your queues with phantom processes. And watch how fast the blast radius compounds. One agent fans out to 3 workers. Each worker retries 3 times on a 30-second timeout. Now a single stalled node is 9 in-flight requests, each holding a context window, each burning tokens. 2 layers deep. That is not a retry policy. That is a self-inflicted denial of service against your own mesh. To survive in production, A2A development requires strict semantic circuit breakers. Every delegated task must carry an immutable, time-to-live cryptographic token and explicit deterministic checkstops embedded directly into the protocol wrapper. So you stop retrying blindly and you start quarantining. A task that fails its checkstops does not loop forever. It gets routed to a dead-letter queue, frozen with its full context for inspection, while the rest of the mesh keeps moving. You bulkhead the swarm so one poison task can never starve the others of compute. If a node cannot resolve a state validation within an exact structural parameter, the execution path must be forcefully terminated, rolled back, and isolated before the loop poisons the rest of the mesh. This brings us to the ultimate infrastructure challenge of the machine majority web: distributed logging and traceability. If a human developer writes a bug into a traditional production stack, you pull up your application performance monitoring tools, trace the stack dump, locate the exact line of broken code, and ship a fix. But if an autonomous mesh network of 5 different agents collaborates to rewrite a production database schema, and something completely breaks at 2 in the morning, who wrote the bug? Which agent hallucinated the input? Which node accepted the invalid schema change without validation? If you don't build a specialized, immutable audit layer right now, debugging an A2A network becomes an absolute impossibility. To map this out, developers are migrating away from basic flat file logs toward strict agentic trace logs built on top of distributed tracing frameworks like OpenTelemetry. Every single thought, token negotiation, and tool invocation must be tied to a permanent, unalterable correlation ID that propagates across every boundary. And there is already a standard for this. You just have to enforce it. The W3C trace context specification defines a trace parent header that carries a trace ID and a span ID across every network hop. When Agent A calls Agent B, it injects that header, and B injects it again when it calls C. One trace ID stitches the entire delegation tree back together. When Agent A talks to Agent B, the A2A header must inject parent-child context parameters that are logged into an append-only, high-throughput telemetry stream. OpenTelemetry now ships semantic conventions built specifically for generative AI, standard span attributes for the model, the token counts, the tool calls, the cost. Wrap every delegation in a span, tag it with those attributes, and your trace stops being a wall of text. It becomes a queryable, structured record of exactly what each agent thought and did. For true non-repudiation, go one step further. Hash the exact prompt and the exact response, and write that digest into the trace. Now no agent and no engineer can quietly claim it said something it did not. The log is not just append only. It is cryptographically tamper-evident. That is the difference between monitoring and accountability. You cannot rely on the agent to log its own errors. The infrastructure hosting the agent runtime must capture the raw system inputs and outputs deterministically. If you don't control the visibility of the transaction trail, you don't control the system. And when the 2 in the morning incident finally hits, this is what saves you. You pull the trace ID and you replay the entire delegation tree, span by span. Every input, every tool call, every handoff. The agent that hallucinated the schema change is no longer a mystery in a wall of logs. It is one highlighted span in a tree. You found the bug because the infrastructure remembered. The era of building isolated, single-prompt AI tools is drawing to a close. The future belongs to distributed, highly cooperative multi-agent mesh systems. But as we hand over orchestration control to autonomous protocols like Google's A2A, our responsibilities as software engineers don't shrink. They scale exponentially. Zero trust starts with identity. On a real mesh, an agent card is signed, and agents authenticate each other with mutual TLS before a single byte of payload moves. No anonymous agent gets to negotiate. If a node cannot prove who it is and what it is authorized to touch, the handshake dies at the door. Then you scope it to the bone. Every delegated task gets least privilege credentials, a narrow, short-lived token that grants access to exactly the one resource the task needs, and nothing else. A compromised research agent should never hold the keys to your production database. The agent card declares the scope. The runtime enforces it. So if you are actively designing architecture for this new machine majority landscape, your workflow requires 3 fundamental changes immediately. First, implement strict semantic circuit breakers. Force explicit time-to-live constraints and deterministic checkstops on every asynchronous delegation loop to kill runaway bot processes. And cap the spend, because autonomous loops cost real money. Every delegation tree carries a hard budget, a ceiling on tokens, on dollars, on wall clock time. Cross it, and the whole branch is killed and rolled back. An agent that cannot stop itself must run inside a box that can stop it for it. Second, build non-repudiation logging. Enforce distributed tracing across every single agent boundary using unalterable parent-child correlation tokens. Third, enforce zero-trust network isolation. Treat every incoming agent request from the mesh as an unverified, untrusted input. Sandbox the tool runtime environments and validate every schema execution as if it came from a hostile entity. And for anything with a real blast radius, a production deploy, a schema migration, a payment, you keep one human gate, not inside every loop. That does not scale. But at the boundary where a mistake is irreversible, the mesh pauses at input required and waits for a person to sign off. Automate the work. Gate the consequences. The infrastructure is shifting right in front of us. The lines of code are negotiating with each other, and the mesh is expanding. You can either let your systems cascade into untraceable, non-deterministic chaos, or you can build the zero-trust architecture that governs the future. Govern your platforms, isolate your runtimes, control the parameters. I'll see you in the logs.